The family of Uranus has expanded. Just a few months ago, astronomers announced the discovery of a previously unknown moon orbiting this distant ice giant. This exciting revelation increased the number of Uranus's known moons from 27 to 28. The newly discovered satellite, christened with the provisional, is a tiny marvel of the cosmos, measuring only 8 kilometers across. It holds the title of the smallest known moon of Uranus to date. But while this tiny addition has sparked excitement among space enthusiasts, the mysteries surrounding Uranus have intrigued scientists for decades. Much of what we know about this enigmatic planet is based on data collected during Voyager 2's historic flyby in 1986. Although this data is nearly 40 years old, it remains a treasure trove of insights and surprises. Before we dive deeper into these fascinating revelations, don't forget to subscribe to our channel. Hit the notification bell to stay updated on the latest discoveries about our universe, and give this video a thumbs up if you love exploring the mysteries of space. Voyager 2's encounter with Uranus in 1986 marked humanity's first and only close-up look at the ice giant. Despite its age, the data collected during this flyby continues to shape our understanding of the planet and its surroundings. Among the most puzzling findings was the detection of a surprisingly strong radiation belt within Uranus's magnetosphere. This belt contained energetic, fast-moving electrons, with intensities comparable to those found in Jupiter's extreme magnetosphere. However, unlike Jupiter, Uranus's surrounding environment appeared to lack the plasma sources needed to sustain such intense particle activity. This raised a critical question: where were these high-energy electrons coming from? Scientists expected that the planet's 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, would release water molecules into space, which would then be ionized by the magnetosphere. Yet the observed conditions didn't align with these expectations. For decades, experts struggled to make sense of this apparent contradiction. Only recently did a breakthrough come to light, thanks to a re-examination of Voyager 2's data. A team led by Jamie Jinsky from NASA's Jet Propulsion Laboratory revisited Voyager 2's radiation and particle density measurements. Their analysis revealed a critical detail that had been overlooked for decades. Just before Voyager 2's flyby, a powerful solar storm swept through Uranus's vicinity. This solar event compressed the planet's magnetic field and ejected surrounding plasma into space. In doing so, it filled Uranus's radiation belt with high-energy electrons, creating the puzzling conditions observed by the spacecraft. In essence, Voyager 2 had encountered Uranus during a highly unusual period. Such extreme conditions are estimated to occur only about 4% of the time. Had the spacecraft arrived a few days earlier, it might have observed a completely different magnetospheric environment. While this discovery has resolved one mystery, it has also highlighted how much we still don't know about Uranus's magnetic field and its broader dynamics. Uranus's magnetic field is one of the most unusual in the solar system. Unlike Earth's magnetic field, which has 2 distinct poles, a north and a south, Uranus's field is highly irregular. It is tilted at an angle of 59 degrees relative to the planet's rotational axis and is offset from the planet's center. This bizarre configuration results in a magnetic environment that is both asymmetric and highly dynamic. But how is such a magnetic field generated? On Earth, the magnetic field is powered by convection currents in the planet's liquid outer core, which acts as a geodynamo. However, this process requires a certain minimum thickness of the convective layer, a condition that may not be present on Uranus. Uranus's interior is composed of a solid core surrounded by a thick layer of water, ammonia, and methane. This mixture is believed to be electrically conductive, making it a potential candidate for generating a magnetic field. However, models suggest that the convective currents responsible for Uranus's magnetism may be confined to a thin layer relatively far from the planet's center. This could explain the non-dipole nature of its magnetic field. One of the most fascinating theories about Uranus involves the possibility of diamond rain. Deep within the planet's interior, extreme pressures and temperatures are thought to break down methane molecules, releasing carbon atoms. These atoms are then compressed into diamond-like structures, which may sink toward the core in a dazzling rain. This process could play a role in Uranus's unique magnetic field and thermal dynamics, but much remains to be studied. The discovery highlights the potential for finding more moons around Uranus. Many of these smaller satellites may have eluded detection due to their diminutive size and the planet's vast distance from Earth. As technology advances, future missions and telescopes could uncover additional members of Uranus's moon family, providing new insights into the planet's formation and evolution. Despite its scientific importance, Uranus has been largely overlooked in planetary exploration. However, this may change in the coming decades. NASA and other space agencies have proposed missions to study the ice giant in greater detail. These missions aim to investigate its atmosphere, magnetosphere, and moons, as well as the intriguing processes occurring deep within the planet. The James Webb Space Telescope, JWST, has already revolutionized our understanding of Neptune, and it holds similar promise for Uranus. By observing the planet in infrared wavelengths, JWST can provide unprecedented insights into its atmospheric composition, temperature variations, and cloud dynamics. Such observations could also help refine our models of Uranus's magnetic field and internal structure. Studying Uranus is about more than just solving planetary mysteries. It's about understanding the broader processes that shape our solar system and beyond. As an ice giant, Uranus represents a category of planets that is common in the universe but poorly understood. By studying Uranus, we can gain insights into the formation of other planetary systems and the potential habitability of icy worlds. From the discovery of a tiny new moon to the resolution of a decades-old mystery, Uranus continues to surprise and challenge us. As we look to the future, the prospect of new missions and observations promises to deepen our understanding of this enigmatic planet and its place in the cosmos. Thank you for joining us on this journey through the wonders of Uranus. Don't forget to like, comment, and subscribe for more captivating explorations of the universe. Potential new discoveries with upcoming missions. Uranus, one of the solar system's most mysterious and enigmatic planets, holds an abundance of secrets just waiting to be uncovered. Despite its scientific significance, this ice giant has remained relatively unexplored since Voyager 2's flyby in 1986. However, the tides are changing, and the scientific community is rallying to prioritize a dedicated mission to Uranus. Let's delve into what such missions could reveal and why they are crucial for our understanding of not only Uranus but also planetary systems beyond our own. The idea of a dedicated Uranus orbiter and probe mission has gained significant traction in recent years. NASA's Decadal Survey, which sets priorities for planetary exploration, has identified Uranus as a top target for future study. The proposed mission would likely consist of an orbiter equipped with a suite of advanced instruments and a probe designed to descend into Uranus's atmosphere. Here's what such a mission could uncover. Uranus's atmosphere is composed primarily of hydrogen and helium, with traces of methane that give the planet its characteristic pale blue hue. However, beyond this basic composition, much remains unknown. A probe could directly sample the atmosphere, measuring the abundance of heavier elements and isotopes, which would provide critical clues about the planet's formation history. Additionally, the probe could study the vertical structure of the atmosphere, revealing information about cloud layers, temperature gradients, and weather patterns. Uranus's extreme axial tilt likely creates unique atmospheric dynamics, including peculiar seasonal variations. Understanding these processes could offer insights into how planetary atmospheres behave under extreme conditions. Uranus's magnetic field is among the most unusual in the solar system, and scientists are eager to understand its origin and behavior. An orbiter equipped with a magnetometer could create detailed maps of the planet's magnetic field, revealing how it interacts with the solar wind and its moons. This data could help scientists refine their models of magnetic field generation, shedding light on the processes occurring deep within Uranus's interior. One of the greatest mysteries of Uranus lies in its internal structure and thermal dynamics. Unlike Neptune, which radiates significant heat from its interior, Uranus emits almost no excess heat. Why this is the case remains a puzzle. Instruments on the orbiter could measure the planet's gravity field and analyze its shape, providing indirect evidence about its internal composition. Such data could help determine the thickness of the layers within Uranus and whether they contribute to its unusual magnetic field. Uranus's 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are intriguing worlds in their own right. Observations suggest that some of these moons may harbor subsurface oceans beneath their icy crusts. For example, Titania, the largest moon, has geological features that hint at past or present internal activity. A future mission could include instruments capable of detecting subsurface oceans, such as ice-penetrating radar or magnetometers sensitive to induced magnetic fields created by salty water. The discovery of such oceans would raise exciting astrobiological questions, as these environments could potentially support microbial life. While a dedicated mission to Uranus may still be years away, the James Webb Space Telescope, JWST, is already providing tantalizing glimpses of what lies ahead. Equipped with advanced infrared capabilities, JWST is uniquely suited to study the ice giants from afar. Here are some of the key observations JWST could make. By observing Uranus in infrared wavelengths, JWST can penetrate the planet's cloud layers and reveal information about its lower atmosphere. This could help scientists identify previously unknown chemical compounds and understand the processes shaping Uranus's weather and climate. JWST's ability to detect heat signatures makes it an invaluable tool for studying Uranus's thermal structure. By mapping temperature variations across the planet, JWST can provide clues about internal heat transport and atmospheric circulation. Uranus's ring system, while less prominent than Saturn's, is still a fascinating feature. JWST can analyze the composition of these rings and track their dynamics over time. This could reveal how the rings interact with Uranus's moons and magnetosphere. Exploring Uranus is not just about understanding one planet, it's about unlocking broader truths about planetary science. Here's why studying Uranus matters. Uranus and Neptune are the only ice giants in our solar system, and they represent a class of planets that is common in the universe. By studying Uranus, we can gain insights into the formation and evolution of similar planets around other stars. Uranus's unique characteristics, its extreme axial tilt, lack of internal heat, and unusual magnetic field, challenge existing models of planetary formation. By studying these features in detail, scientists can refine their theories and apply them to other planetary systems. The discovery of subsurface oceans on Uranus's moons would have profound implications for the search for life beyond Earth. These environments could provide the conditions necessary for life to thrive, even in the cold outer reaches of the solar system. The exploration of Uranus could inspire a new generation of scientists, engineers, and space enthusiasts. As we push the boundaries of what is possible, we pave the way for even more ambitious missions in the future. While the scientific potential of a Uranus mission is immense, it is not without its challenges. Uranus is located at an average distance of 2.87 billion kilometers from the Sun, making it one of the most remote targets for planetary exploration. Here are some of the hurdles that must be overcome. Reaching Uranus would require a journey of at least 13 to 15 years, depending on the trajectory and propulsion system used. This necessitates the development of spacecraft that can remain operational for decades. At such great distances from the Sun, solar power becomes impractical. Future missions would need to rely on advanced radioisotope thermoelectric generators, RTGs, to provide the necessary power for instruments and systems. The vast distance to Uranus means that signals take over 2.5 hours to travel one way. This delay requires spacecraft to operate autonomously for long periods. Uranus's harsh radiation environment and frigid temperatures present additional challenges for spacecraft design. Instruments and systems must be carefully shielded to withstand these conditions. The exploration of Uranus represents a bold new frontier in planetary science. With proposed missions on the horizon and the James Webb Space Telescope already providing groundbreaking observations, we are poised to uncover the secrets of this enigmatic ice giant. From its exotic magnetosphere to its mysterious moons, Uranus offers a wealth of scientific opportunities that could reshape our understanding of the solar system and beyond. By venturing into the unknown, we not only satisfy our innate curiosity but also push the boundaries of human knowledge. The discoveries that await us at Uranus could inspire generations to come and remind us of the limitless potential of exploration. Stay tuned for updates on this exciting journey. Don't forget to like, subscribe, and share this video to support our mission of bringing the wonders of the universe closer to you. Thank you for watching.